All right, today we're heading out to an oil rig. You know, one of those incredible marvels of complex engineering. We're going to uncover a simple, decades-old digital language that, believe it or not, keeps the whole thing running.
So let's dive right in with a question. A modern drilling rig is just a beehive of activity, right? You've got all these super high-tech systems working at the same time. Systems for steering, for monitoring, for pumping, and they're often made by totally different companies. So how on earth do they all coordinate with each other?
Well, in the past, and honestly even today, each piece of equipment was basically its own little island of control. The measurement while drilling tool spoke its own proprietary language. The electronic data recorder spoke another. And getting them to work together to create one clear picture of the operation, that was a massive headache.
So the solution came way back in the 1980s. It was this simple, really elegant standard that's still a huge deal today. It's called Wits. And you can think of it as a universal translator for all this crucial well site data.
Now, WIT stands for Well Site Information Transfer Specification. The whole goal was to create a common format, a shared language, so that when different companies and their equipment showed up on a rig, their computer systems could just talk. No need to write brand new software every single time.
And here's what's so fascinating. You've got more complex standards now, like WITS-MEL. But the most basic version, Level 0 WITS, is still king. And why is that? It's because it is just incredibly simple, super effective, and you can actually read it yourself. It just works.
Okay, so how does it really work? Let's zoom all the way in and break down the structure of a single WITS data packet. This is really the heart of the whole system.
You're gonna love how simple this is. Every single packet is framed by a start marker, that's just 2 ampersands, and an end marker, which is 2 exclamation points, AA. Everything sandwiched in between is the actual data, with each piece of info getting its own line.
Now, the secret sauce is this 4-digit code you see at the start of every data line. It's broken into 2 parts. The first 2 digits, RR, are the record identifier, and the second 2, II, are the item identifier.
And this table just lays it all out perfectly. The record tells you the category of the data. So for example, 01 means general time-based data. Then the item pinpoints the exact measurement inside that category. So 08 means depth of bit. Put it all together, and the code 0108 tells any system listening, hey, the number that comes next is the measured depth of the drill bit. So simple, but so powerful.
Okay, we've got the packet figured out. But how does that little bundle of information actually get from one system to another on a noisy, busy rig? Well, there are basically 2 main ways this data gets sent.
So the first method is synchronous. Think of it like a phone call. One system has to actively ask for data, usually by sending a little dummy packet, to get a response back. The second method, which is way more common, is asynchronous. This is much more like a radio broadcast. Systems just constantly stream their data out, say 1 packet every second, and other systems just listen in and grab the information they care about. All right, so we've gone from the big, chaotic picture of a rig all the way down to the tiny little data packet, and now we're zooming back out. Why does any of this really matter? What's the real-world payoff here?
It matters because this constant, reliable stream of simple data packets lets operators in a control room, a room that could be right there on the rig or literally halfway around the world, see exactly what's happening miles underground in real time.
And this isn't just about collecting data for fun. This information is what allows engineers to make critical, split-second decisions. They can steer the drill bit with incredible precision to follow a geological formation, they can spot a dangerous pressure change that might signal a huge problem, and ultimately, it just makes the entire operation safer and way more efficient.
So in an age where everything is getting more and more complex, the story of WITS is just a powerful lesson. This simple, tough-as-nails protocol has outlasted so many more advanced systems for one simple reason. It's good enough. It does its one job perfectly, and that's all that matters. It really makes you wonder, doesn't it? In our own work, where else is the simple, elegant solution hiding in plain sight?